Good afternoon. My name is Jeremiah. Thanks so much for coming to my talk. I hope everyone here knows that this is a talk about the perils of workflow management, not one of the machine learning talks that's taking place right now. So if you want to take a moment, reevaluate the room you're in, that's totally fine. For the rest of you, I'm really happy to be here as one of the representatives of our DC data community. I have spent most of my career in various forms of data science, usually in finance, usually in risk management. A few years ago, I became a PMC of Apache Airflow, and this year I formed a software company called Prefect here in DC. And I also want to mention I've had a long, very friendly relationship with a company called Quantopian. Some of you may have attended James's talk this morning on using Airflow in production. So James is an SRE at Quantopian, and he's a really fantastic resource if you want to talk about deploying Airflow. In fact, the first person who ever saw our Prefect work was the head of data science at Quantopian, so I think incredibly highly of their company. However, I do want to give some fair warning that this is going to be a very different type of talk than James, and the inspiration for today's talk actually came from an error message. Task failed successfully. The more I thought about this, first I thought it was funny, and then I really liked it because this is sort of what I do. I'm a risk manager, and more recently I build workflow software. So my job is to make sure that when failure happens, it is handled correctly. But even so, what does it actually mean to fail successfully? And maybe more importantly for all of you, how do you turn that into actionable advice? So I think we should start with the basics. What is workflow management? It's a good question. Here's what I think. In a very simple sense, workflow management is when you have things you want done and you put a system in place to make sure they happen. And that's it. Our team uses the terms positive and negative engineering to differentiate between these two types of work. Positive engineering is the work you actually want to do. Negative engineering is everything you have to do to make sure it gets done. That's the error trapping and handling, the type coercion, the data serialization, the infrastructure, all of that stuff. Most data scientists and data engineers want to be writing positive code, and I believe it's the role of a good workflow system to support them by taking on the negative side. In that sense, negative engineering is a form of risk management. Now, negative engineering requires you to anticipate and defend against all the possible ways your system could fail, or in a more general sense, behave. Some pessimists might say that's impossible, and others miss the point by assuming it's easy. They say, well, if you don't want errors, just write better code. And in my past life, that would have been like saying, oh, you don't want to lose money, just buy better stocks. It's easy to say, it's very, very hard to do, and it's frankly silly either way. As a risk manager, I can tell you that this is very doable in the right framework. So to illustrate what negative engineering actually entails, let's walk through an example. So here's finally some Python. This is a simple made-up task that I want to do, and since it's what I want to do, it's a form of positive engineering. But now we are putting on our risk management hats and we start thinking about negative outcomes. How do we defend against failure? And so the first thing that most people do is they trap the error, right? It's very easy, it's very straightforward. Do this, if it doesn't work, raise a helpful error. Now a cynic might note that this just replaces one error with another, and while that's true, it could also be a case of better the error I know than the error I don't. In either case, we can do better, and so most people will move on to retries. And so here we've added some logic to retry the task up to 5 times, and it's going to wait 10 minutes between each attempt in case the system needs to cool down. So we feel good about this, we put it into production, and immediately it starts failing. Something is wrong with the function arguments, we don't have a way to replicate it locally, so let's debug it in production. And the way we're going to do this is with very specific errors when our arguments have the wrong type. So have we actually solved a problem? No. But do we feel better about it? Maybe. What we have done is taken a situation we already knew was bad and added an explicit hook to find out when it happens. It may seem silly, but that is a totally valid negative engineering exercise. No one has ever complained about having too much information. But now it turns out that our task is hogging resources, and when it sleeps for 10 minutes, it is still running. So our full failure cycle takes almost an hour. Our team wants us to do better, so we're going to retry asynchronously. And now, in addition to writing error trapping code, we're going to write error trapping infrastructure, which I'm obviously not going to bother to write here, but our function now returns these API-like status messages so that some other system, presumably, can manage it and retry it appropriately. And it turns out we're not even done with that. Sometimes you might remember that this function, which I don't even know where it is here anymore, was doing 1 divided by a result. And, every now and then it turns out that that result can be 0. So we need to introduce a special handler for that 0 case, lest that error take down our whole system. So let's take a step back and see where we started and where we ended up. This is what we wanted to do. This is what we had to write to actually do it. This is the positive engineering. That's the negative engineering. So yes, my example is extremely contrived, but if you think it's unrealistic, then you need to talk to more data engineers. For this example, we worked with a single task to control issues that might arise in only its execution. And that's great, but even that doesn't justify a full workflow management system. Workflow managers become much more important when we start to deal with the dependencies between tasks. And I would argue that what takes a series of function calls and graduates it to a workflow with a capital W is the fact that some process is monitoring and managing the full state of the system. Because while any task can, in theory, look out for its own state and its own failures, we need something to ensure the integrity of the system as a whole. And in order to do that, we have to know how to work with failure. The central question is, if a task has an error and no one is around to depend on that task, then does anyone really care? Did it actually fail? But if someone does depend on that task, whether it's a person or another task, then all of a sudden handling that failure becomes critical. And so this idea of failing successfully is not just about reporting that an error happened, it's about defining the behavior of the system once that error takes place. And this is super important because task failure should not automatically mean system failure. Failing successfully means that failure is a part of our system. It is a state, just like success, that we can work with, that we can react to, and that can drive business logic. If you, the designer, want to apply meaning to that failure, then that's totally fine. Maybe you want the workflow to stop as soon as it has a problem. Maybe you want it to stop only after 10% of tasks fail. Maybe you expect failure and want to react to it every single time. All of those are totally valid. It's not for the workflow system to decide whether failure is necessarily good or bad. Its job is to reveal it, promote it, and make it available for any business purpose. And that is how you fail successfully. Now, what happens when we don't embrace failure, when we treat it as an outlier? Workflow systems are often victims of something that in my finance days we called wrong way risk. Wrong way risk is the idea that your exposure to a bad outcome is exaggerated when the bad outcome occurs. And the classic example is that you buy insurance against some natural disaster. And one day the disaster actually happens and you go to file a claim and you find out that your insurance company only sold policies to people in your neighborhood. So everybody's making a claim and the insurance company is bankrupt and you wind up with nothing. So you had wrong way risk. You thought you were insured, but your insurance turned out to be negatively correlated with the thing that you were insuring against. Workflow management systems introduce wrong way risk when they treat failure as an outlier or an afterthought. By not taking it seriously or not providing first-class tools for working with it, they cripple themselves at exactly the moment that they should be most useful. And the proof of that is simple. If you could guarantee that your workflow would run perfectly, you don't need a workflow manager at all. Just put in a script and run it whenever you need it. It's only as we start to introduce some probability of failure that the workflow system becomes really important. It's how we're going to deal with those failed states. So therefore, if the workflow system treats failure as unexpected, it is least equipped to deal with the situation that we need it the most, and that is wrong way risk. Now, a lot of people assume they can control this by building robust data pipelines, but usually they worry exclusively about the data, and you talk about data lineage and data latency and data storage, but you never hear about the workflow system itself collapsing. And that's because of a rather massive assumption that we all make, that our workflow systems are perfect, that they handle themselves the right way, and that they do not fail. And I wish I could live in that world, but I have touched almost every line of Airflow's code, and I can assure you that there's nothing magic about a workflow system. It has a strength, it has a weakness, and it doesn't care how much time you spent on your ETL checks. It will fail if you don't use it the right way. So you haven't set yourself up to fail successfully. You haven't set yourself up to succeed in any way at all if you don't play to your workflow system's strengths. We can see how this will play out. This is what a workflow system is supposed to do. It's supposed to protect against problems. That's the negative engineering aspect. It's supposed to promise that work will get done. That's the positive engineering side. And of course, it needs to provide us with the tools that we need for working with the results of those tasks, good or bad. But what really happens is quite different. First, workflow systems compromise. In order to make good on their promise to protect against failure, they limit what they let you do. Because you can't do very much, they don't have to defend against very much, and they minimize the number of things that can go wrong. So the first sin is the compromise. The second sin is the cheat. The cheat is how we get around the compromise. If your workflow system is compromised because it doesn't handle retries, it's no problem, just write a script like I did before that does the retry yourself. At the end of the day, it's all code, and you can do whatever you want. The only question is whether your code complies with the expectations of your workflow system. So that might not seem like a problem, but it can be really, really dangerous. You end up effectively running two systems, neither aware of the other, and without any common vocabulary for understanding what the other one's doing. And that leads to the third sin, corruption. All workflow systems are designed with a philosophy of how workflows should behave. If it's not written down, then it's expressed in what kind of tasks they can run and what the contract is that those tasks fulfill. The reason the previous sin was called cheating is because we were forcing the workflow manager to do something contrary to its philosophy, contrary to what it was designed to do, and that corrupts it. How do you record a task's retry attempt if you don't know what a retry is? How do you decide if a task is ready to run based on data if you don't track data dependencies? How do you resume from a failed state if your system was designed to exit on failure? This is the most common type of Airflow bug we see. It happens when you try to do something that Airflow doesn't really understand but lets you do anyway. The system gets corrupted, recovery can be impossible. How would you like to see some examples? First up, something called XComs. One of Airflow's compromises is that tasks communicate purely via state, in this case, success or failure. And therefore, there is no way for them to exchange data or information. And people kept coming up with ways to get around this. So a few years ago, we cooked up something called XComs, which stands for cross-communication. To a user, XComs look like a first-class way to move data between tasks. But from Airflow's point of view, XComs are a hack. They're definitely a cheat. Under the hood, and don't worry too much about this, an XCom is just a way for tasks to impersonate an admin user and write arbitrary data to the Airflow database. Tasks push or pull information from the database, which creates strong data dependencies between tasks. And these data dependencies can exist between two tasks, between two DAGs, or even between a single task and a past or future version of itself. It is a very rigid and error-prone form of dependency, and the kicker is that Airflow, the system we use to manage dependencies, has no idea it exists. It has no vocabulary to describe or enforce a database dependency. And so the single most common Airflow bug we see is users who have used XComs to hack strong data dependencies into a workflow system that doesn't track data dependencies. What this means is that if a task ever fails, and therefore doesn't push the XCom, the next task is also going to fail, and Airflow has no idea why, because we went outside the system. It leads to a very frustrating chain of failures. Even worse, XComs are serialized into the Airflow database with no way to delete them and no expiration. So if you're processing a 10 gigabyte data frame and you pass it through 100 tasks, then every single run is generating a terabyte of permanent storage, which is just, it's sort of insane. And it all begs the question, should I use XComs? And the answer is probably not. And the punchline is that that's me. Okay, I wrote XComs about 3 years ago because I was frustrated by this problem. And I own this cheat, and I regret it. And the truth is, I don't think Airflow is usable for data science without XComs. I think you need to move data around. Data dependencies are just too important in the modern data stack. But when I designed these XComs, I was using them to pass around tiny little bits of transient information. And I remember Maxime, who's the original developer of Airflow, telling me that this system was prone to abuse, but I didn't listen. I thought this was too important to include in the system. But sadly, as I said, it's become one of the largest sources of untraceable bugs in the Airflow world. So watch out for your XComs. The next thing I'd like to talk about is something called the branch operator. There's Dwight Schrute. The branch operator allows us to include branching logic, which is pretty fantastic. We need that a lot of the time. And it's also pretty amazing because it's not possible in Airflow. The same compromised functionality that led me to make XComs says that there's no way for a single task to tell multiple downstream tasks that one of them should run and the other shouldn't. All it can do is return success or failure. But branching is important, so what do? And of course we cheat. We don't need to look too closely at the code, but if you do look in the code, you'll see that the task is calling a method called skip. And that seems kind of reasonable that it would call this method that lives on itself until you ask, well, why is this task skipping itself? And the answer is, it's not. It's actually skipping the task that goes after it. So the skip method is another backdoor into the Airflow metadata. This task is manipulating the state of a task that hasn't been evaluated yet. And from a data integrity standpoint, that should horrify you. Right? Airflow, the system that tracks dependencies and enforces contracts between tasks, is letting a task impersonate an admin and mess around with other tasks. It's a completely untraceable form of dependency, and it's the most pure violation of Airflow's philosophy that I'm aware of. But it's incredibly useful, so we forgive it. And in the interest of time, I'm going to move through some of the text, but these will be available later for you to read. The last example that I want to run through in detail is about the intersection of Airflow's state and business logic. So this isn't so much a compromise, actually, as it is a choice. Remember that a good workflow system is supposed to track state, but be agnostic to how it's used for a business purpose, agnostic to what it signifies. And that's what lets us fail successfully. We elevate state to a place where you can make decisions based on it. So this is an interesting situation. This is a workflow that has two tasks. One of them is very important. It does something that you care about. And the other one just cleans up if the first one has a problem. So on the left, this is a situation where the important task was successful, and we didn't even bother running the cleanup. And I think we all agree with Airflow that that is a successful run of this workflow. But on the right, we have a situation where the important task failed, and the cleanup task was successful. Now, Airflow thinks that this run was successful. And to be honest, I don't know if it was or wasn't. That's up to the person who designed it. Maybe they only care that the workflow ran, and so yes, they would like to see this as a green light on their dashboard. But I can easily imagine the situation where someone cares deeply about the important first task running, in which case they'd like to see this as a failure. But Airflow does not give you a choice. Airflow has it hard-coded that DAG state is always determined by the last tasks in the DAG. So this is a design failure. This means that our workflow system is not capable of reflecting business logic, and therefore we cannot fail successfully. The system is corrupt. And I'm going to, again, skip some text in the interest of time, and we'll just move very quickly, if you're interested, through a couple of other quick examples. People use Airflow's global variables in place of parameters, which just creates a very stateful mess. People abuse the fact that Airflow reruns a DAG every single time it runs a task to introduce DAGs that change while they're running, which I don't even have to tell you how horrifying that should be. Off-schedule runs. Airflow used to not support off-schedule runs. We eventually sort of found a way to make it do it, and we found that this assumption was so baked into the system that both the scheduler and the UI broke as soon as we ran something off schedule. In particular, the schedule was working by adding an interval to the most recent run. So if you had something ticking along every hour, it was totally fine. Then all of a sudden, if you ran something on the half hour, the scheduler would start adding the hour to the half hour time and keep going from there. So again, the idea is that these are not impossible. You can make the system do whatever you want, but if you don't respect the assumptions of the system, you're going to end up in an unexpected place. And the last one I'll talk about is that Airflow's database has a unique constraint on a DAG and its execution time, which means that you cannot run a DAG twice at the same time. It doesn't support the concept of simultaneous runs of the same DAG. Now, if you live in Airflow's world, that's totally fine. That makes sense. If you live in my world where I want to run workflows all the time, no matter what, for any circumstance, that makes no sense at all. So that's a big problem to me. I think it's extremely important for me to note that these problems did not start with Airflow, and they are not unique to Airflow. I just happen to know them very well in an Airflow context from solving users' problems. I want to repeat that all workflow managers have strengths and weaknesses, and identifying these weaknesses doesn't automatically mean it's bad. It's just a benchmark for you to measure your appropriate use of the tool against. And we can see how this has played out through history. Right, so in the beginning, there was cron. And in fact, cron, I was very surprised to learn, dates all the way back to 1987. And I'll bet that every single person in this room has written a cron cheat, because cron makes the compromise, of course, that there are no dependencies. So if you want two things to run in sequence, you schedule one for midnight, you schedule one for 1 a.m., and you hope they work. That's the cron cheat. And after cron, we can move pretty quickly. This is Uzi, which is cron in Java and XML. This is Azkaban, which is cron with dependencies. This is Luigi, which is cron with dependencies that are based on side effects. Spark is an interesting one to mention. It doesn't feel like it fits in this pattern of data engineering workflow managers, but if you have spent enough time in both the data engineering world and the data science world, you'll quickly remember that Spark and other tools like it, including Beam, Dask, even TensorFlow, these are just ways of describing computational graphs and moving data or some state through them. So it just happens that Spark passes data instead of state, but it's the same idea. And last but not least, of course, we have Airflow, which I would basically describe as cron with a database. So the question is, what have we learned from this history of workflow innovation, which, by the way, I think stopped in 2015? This is a quote from the creator of Luigi. He said, all workflow engines kind of suck, including Luigi. The question is, well, why? Why do they have to suck? And one answer is that they were originally created to solve a specific problem at a specific company, which means that while we can today point back and say, yeah, they were compromised, they weren't compromised in the moment, they were appropriate to the task at hand. It's only once they were open sourced and attempted to be widely applied that these compromises became evident. And in the absence of a modern alternative, they've become weighed down by all of these cheats that I've been enumerating today. A common response from the authors of these platforms, including myself, is that users should just write idempotent tasks. Does everyone know what idempotency is? It's basically the idea that if you run something multiple times, it'll only cause an action once. So this is sort of like the get out of jail free card of data engineering and data engineering workflow authors, because of course, if you have an idempotent task, it'll work. You could use cron and just spam a server every 2 seconds with a bunch of idempotent tasks. You don't need a workflow manager. So it's like, yeah, this is true, but does it really matter? Is it practical? And the answer is no, it's not. So I'd like us, to be clear, idempotency is good, but we need to live in the real world where it's unlikely and possibly impossible, and perhaps impossible. And so instead of pretending that people can write perfect code, let's acknowledge that they write bad code and see what we can do to support them. In today's talk, I've shown that these workflow managers, they commit these same basic sins over and over. And because they implement compromised, limited functionality, they end up cheating to implement the features they want. How can we overcome this? We need to start with what users actually want to do. And if you're the users in this room, what you want to do is you want to write Python. So this is what the simplest ETL script I can imagine looks like in Python. And this is an example of positive engineering. This is what you want to do. How would we design an idealized workflow system around this code? Well, if you think about it, almost everything we need is already here, right? We know what the tasks are. We know what the workflow definition is. We just need a way to communicate this to this magic system that we're inventing. And the way we need to do that is by creating entry points for our negative engineering hooks. So here's what that might look like. And if you don't see the difference, I'll highlight it. All we've done is introduce these decorators, which will tell our system, these are the tasks. They're going to run, keep an eye on them, manage their state, manage their data dependencies. And then down here, we've created a workflow. We're saying, hey, this is my computational graph. It's in Python, and I want you to pay attention to what happens. This is going to be the workflow that we run in the future. And that's it. I don't have to explain anything else. In theory, it's all here. So there's one last thing that we need, and that's to import prefect. So this is real, this works today. This is actually our hello world, and this is the first time that we've ever shown it publicly, which is kind of cool for us. My team has worked incredibly hard to build this API, not to mention the system that powers it, and we're very excited that we're going to be open sourcing it in the very near future. And I promise that it fails more successfully than anything you've ever seen. In fact, the most important thing that we did with Prefect was that we allowed it to fail successfully. Prefect will track the state and result of every task in your workflow and let them depend on each other in a variety of ways. We use these rich state objects, the currency of the system, and we allow users to apply semantics to those objects. Don't worry, we have sensible defaults, so you don't actually have to do anything more than what I showed a moment ago if you don't want to. So a traditional data pipeline implemented in Prefect would ignore state and just pass data. A more complex pipeline might use the state to make decisions, maybe to kick off a cleanup job, and a really out there workflow could actually let failed tasks return data, for example, their own exception, and use that to drive diagnostics downstream. As we think these abstractions become incredibly powerful, and they are only possible because the system is agnostic to its application, it is failing successfully. And I want to mention that under the hood, we are using Dask to drive pretty much all the execution. We think that Dask is one of the best tools out there, and it was actually when I really got my hands on Dask as a data scientist that I thought for the first time that something like Prefect might even be possible, and we'll have a lot more to say about that very soon. So one last thing, since I've been talking a lot about Airflow today, I spent years on Airflow. It's a very important tool to me. It's a very important tool to the data engineering community. I do think it has some flaws. Prefect does not share any code with Airflow, but it will run Airflow for you. And so we have some partners who are using Prefect to modernize their Airflow stack without losing any of the work that they put into building it. So I want to thank you all for coming to my talk about failure. If you'd rather talk about success, we're working with a number of partners to develop Prefect, and if you're in this room today, we would love to work with you. You can reach us at this address, which is hello@prefect.io, or come find us outside. We're the guys who have been handing out free Compass coffee all day. And since I think we have a little bit of time left, do we? Yeah. Yeah, then I'm happy to take some questions, if there are any. Or if there aren't. Yes?
Oh, 1 second. You work here.
Hey, Aaron Amadia, Capital One. So the question I have is, when we look at some of these workflows, obviously there's all the problems that happen operationally, and then there's all of the things and the challenges that we face while we're trying to develop them, trying to figure it out, debug it, piece it through. How can you compare and contrast what you're promising so far with Prefect in terms of, as I am building a workflow, what the debugging process looks like, getting into the state, being able to develop locally versus sort of that deployment stage?
So this will run on your local machine. If you want to run it in a synchronous process so you can actually put breakpoints and inspect them, that's totally fine. We do that for our own testing. If you want to run it in a local Dask cluster or even using a Dask synchronous executor, that's totally fine. And then you can also deploy this into a cluster very easily. But these are just functions. They're exposed in this form to you, and they will do whatever it is that you want. One of the core design principles of Prefect is that the tasks themselves are black boxes. We don't really care what's in them. We're agnostic to it. We actually don't even receive the code from our partners. It's sort of an important privacy barrier that we've created. So you can do whatever you want, interact with your systems however you want. We really don't care, frankly. So if you need to debug this locally, you just call it as a function. You don't even have to run the flow. It's not tied to anything unless you want it to be.
Okay. So, I would have to explicitly pull that state out and dump it somewhere if I was debugging, for example.
So this is actually, we worked very hard on this, so I like to show it off. This is sort of our functional API. It's not actually running the functions, it's just building a computational graph similar to any deep learning tool that you might use today. We have a fully class-based system behind it, just like Airflow. If you want to call set upstream, if you want to manipulate tasks and edges directly, you absolutely can. If I had added a line here that was flow.run, you would receive back a dictionary with all of the state objects from all of the tasks in that run. You could manipulate them and examine them and do whatever you want with them. You can even crack open the hood and see how we're working with them. So to be clear, yeah, we have a functional API. We also have what we call our imperative API for more programmatic access. But this is more fun.
Could you talk more about integration with Airflow? I kind of you sounded like you made a promise. So if I keep working in Airflow and then you promise me something, this is better later on, I'm not like hosed in terms of like 6 months of development of like a bunch of DAGs?
So I challenged my team to, oops, did I do that? I challenged my team to translate Airflow into Prefect, which I thought would be rather doable based on my knowledge of Prefect, based on my knowledge of Airflow. We decided not to do that because there are some features of Airflow that we don't support with a direct analog, XComs being one of them. We have what we think is a much stronger data dependency feature that we're showing here. And we didn't want to write translation logic that we would then have to maintain. So we're working with some of our partners, some of whom are actually other Airflow PMCs, who are using Prefect to instrument their Airflow deploys. So you keep your Airflow database running, you keep Airflow running. We have Flow in Prefect, which creates a copy, a one-for-one copy of every task in your DAG, loads it into Prefect so that you can use all of our introspection tools, you can use our API, you can use our UI to examine it and run it. But at the end of the day, it's calling back to Airflow to run your existing system. So we've abandoned the idea of translating it because we just refuse to support some features.
Maybe this is a weird thing to say, but so I used Uzi in my career before, and I'm using Airflow right now. And you know, I've never been a JavaScript programmer, but you see the rise and death of like JavaScript frameworks and visualizations of that. One of the reasons, well, we chose Airflow because of its utility to us, but we also were excited as someone on Google Cloud Platform that they kind of made it a first-class citizen with Cloud Composer. Do you see this world as like the coming and dying of the same way we have JavaScript frameworks, like what's hot right now in terms of workflow orchestration, and it's like next year, like I'm going to be applying for Airflow jobs, and people are like, I don't care about that at all. Are we in that time? Is it just like, are there still like, as you were saying, people make these things and they open source them, then everybody makes a ton of demands about what they should do, and then they're like, that wasn't designed to do that, and they're like, okay, now on to the next one.
I think that's the first time anyone's ever described the workflow manager space as hot to me. I had to beg people to take me seriously when I said that this was even possible. I mean, we've had conversations with people who deny that it's possible until we show them how we did it. Airflow is close to 4 years old now, and nothing has unseated it. And so while it has gained momentum, and to be clear, I am an Airflow PMC. I am extremely excited to see that. I think I have the third most commits of anyone in the world on Airflow. It's an amazing thing, but it's not a hot space. It's not a crowded space. I'm frankly amazed that we see this emergence of an Airflow developer. Like, I'm not sure that's a good thing, to be honest with you. Sort of, my argument here is that the workflow system should fade, right? You shouldn't be an Airflow developer. You should be a developer who happens to use Airflow. Any other questions? Yes?
Are you addressing compute environments here? No.
We've designed our compute to be modular. At the moment, we prefer Dask, and we use Dask running in Kubernetes.
Okay. But you have a situation where certain processes have certain software requirements.
Like, how do you, sorry. I mean, let's suppose you have one step that's got a lot of different software than the next step. Like, how would you address that?
A lot of different dependencies?
Yes,
So,
software dependencies.
yeah, no, it's a good question. Today, the workflow is built as a container with a single set of dependencies. You put them all in, and we're working towards supporting an individual container per task.
Yeah, okay.
Is that a hint? Are we supposed to get out? Okay, I'm happy to take questions as long as there are. Yes?
Here you go. Thank you.
My apologies if you already answered this, but I know many people have found frustrations with distributing Airflow jobs using Celery, just with the complications of Celery and things. What's the story for Prefect around running a cluster where jobs are run across it?
Sure, so that's what we use Dask for. Dask is hands down the best way to do that.
Can you describe that a little bit further, assuming people know, I know about Dask and assuming others do, can you describe how it leverages Dask?
Of course. One of the easiest ways I've found to describe Dask is actually as sort of a pure Python and friendly version of Spark. So Dask is, I think, just an extremely easy way to distribute computation across any number of nodes, whether it's your local laptop or something running in the cloud. It'll take a function, it'll serialize it, it'll run it in the cloud, it'll bring back a result. Or what's really cool about it, and what we'd like to take advantage of, is you can dynamically build yet further graphs from an already running graph. So, I mean, in a nutshell, it's just a very easy way to run distributed computations. Frankly, it's the best I've seen. So we use it for our primary execution engine. It's modular. If somebody wants to write an extension for something else, they absolutely could. You want to go back to Celery, by all means, go right ahead. But we're promoting Dask as our primary executor. Yes.
Do you expose that you're running on Dask at all to the users? Like, do they get to see the Dask dashboard? Is there any exposure of that at all?
It's a great question. So at the moment, no, but not because we've decided not to. We just sort of haven't addressed that question. So it's a good one. We don't hide that we're running Dask. In fact, we would invite users who want to take advantage of the fact that we're running in Dask to just open up a worker client. And we're trying to figure out the right way to create a sort of first-class API where you could still run that locally, effectively, and do your debugging, but also have it work properly in a distributed environment. So we don't hide it from users. We also, at the moment, aren't explicitly promoting it to users. It's just it's an important fact. Anybody else? All right, well, thank you all so much. I appreciate your attention and your time.